All right, we are ready to at least get close to solving some problems involving the sinusoidal steady state. And I want to remind you of some things. First of all, this is the relationship between voltage and current for each of the three ideal basic circuit elements that we've encountered: resistor, inductor, capacitor. And this is what our sources are going to look like. And we talked about how, well, if you have a current that is sinusoidal in nature, it can be written in a form like that, where its phase angle is, we'll just call it theta sub I, and that's going to produce voltage that's going to follow the same sort of sinusoidal relationship, have the same frequency, but its phase angle is going to be different. So these magnitudes or amplitudes are going to be different. Certainly the phase angles are going to be different for these things right here. Well, all of this right here, this is in the time domain. And if we want to solve a problem with sinusoidal steady state, what we have to do is we have to transform to the frequency domain. Okay, and in order to transform into the frequency domain, each one of these elements needs to be transformed. So, for example, when you transform the resistor equation, the relationship between current and voltage in the frequency domain looks just like this. Phasor V is equal to phasor I times R. That's just V equals I times R. But now we're talking about these being phasors here. So this is specifically for the resistor. Okay, now when it comes to the inductor, transformation looks a little different. It looks like this. Phasor V for the inductor is going to be phasor I times J omega L. Okay? Now you may say, well, where did that right there come from? Well, hopefully we'll talk a little bit more about that in a minute. And then for the capacitor, it looks like this. Phasor for the capacitor is equal to phasor I times 1 over J omega C, like that. Okay, now you'll notice all of these in the frequency domain have the same general form. And they're all very linear. And that's the advantage of transferring from the time domain into the frequency domain. Now you transform these things, you already know how to do these hopefully. Phasor I is just I sub m angle theta sub I, and phasor V for the source here is just V sub m angle theta sub V, like that. Okay, well, you can see that they look pretty simple over here. Manipulating them is perhaps another story, but we'll get to that. A little bit of information. This omega L, that is called the inductive reactance, and it's symbolized as capital X sub L. Okay, and it's called the inductive reactance. So we could write this as I times J X sub L, like that. That would be one way to write that. And the 1 over omega C, that's called the capacitive reactance. Like that. And we could write this as I times 1 over J times X sub C, like that. Okay, now a little bit more of information. You notice both of these have a J's attached to them. If you take all three of these elements, I don't mean all three, but if you look at each one individually, the J omega L, the 1 over J omega C, or the R, those quantities there are called impedances. Now, an impedance is nothing but an opposition to AC current flow. That's what it is. So very much like resistance played a role in DC circuits, impedance plays a similar role in AC circuits or sinusoidal circuits. So you can see the resistor behaves pretty much the same way in the frequency domain as it does in the time domain. But the inductor and the capacitor, those are a little more complex. I mean, no pun intended. I didn't mean it that way, but it does make sense. These are complex numbers, so they're a little bit more complex. All right, but if you take each one of these then, and you can say its impedance for the resistor is just R, the impedance for the inductor is J omega L, the impedance for the capacitor is just 1 over J omega C. All three of these are impedances, so in general we'll give impedance a symbol of Z. And Z is going to be a complex number, and Z is impedance. It has units of ohms, just like resistance does. But then we could write every one of these as just V equals I times Z, where these are phasors. Now technically Z is not considered a phasor, even though it is a complex number. It's not considered a phasor. The V and the I are the two things that are considered the phasors here. But Z is going to be different depending upon which element you're talking about then, either the R, L, or C. But that's a general way then to write down all of these relationships between voltage and current for the various elements. Okay, now you might be saying to yourself, all right, well, I know where these came from over here. We've talked about those the entire semester. But how did you jump from this to that? Let me show you a little bit about that right there, okay? So we'll spend a few minutes talking about that right now. Okay, what we're going to do is we're going to imagine that we've got a circuit with each one of these elements in it. So let's start with the resistor first. Let's say that we've got a resistor circuit that's got a sinusoidal source in it, and I is equal to I sub m times the cosine of omega t plus theta sub I. Okay, that's going to be the form of our current. Now, if you take the phasor of that, you know that that's going to be I sub m angle theta sub I, and that's equal to phasor I. Okay. Now, the voltage, the relationship in the time domain is just V equals I times R. All right, well, let's take our I and plug it in down here, and we're going to end up with something that looks like this. I sub m times R times the time varying part, which is the cosine omega t plus theta sub I, like that. Now, let's take the phasor of this, and when we take the phasor of that, we're going to end up with I sub m R times, or angle theta sub I. And what that is that is the phasor for V. Now, what I want you to notice here is that V and I have exactly the same phase angle. Now, what that means is that if you were to plot this, let's say you plotted one of those and it follows some sinusoidal relationship here, and then you plotted the other one, it's going to have a very similar, maybe not the same amplitudes, but it should have this, in other words, the minima and the maxima occur at the same time. It crosses zero at the same time. It does all those things. So that's what is meant by them being in phase. Okay. Now that's what it would look like if you plotted it on a rectangular coordinate system. The sign, and in the time domain, the signs look like that. Or I'm sorry, the cosines, the sinusoidal parts look like that. They're in phase with each other. However, if you plotted that in the, let's say, complex plane, and you plotted them as a phasor, then phasor I could be right there. That angle right there, that's omega t plus, the theta sub I. That's that angle. And as t increases, in other words, as time goes by, this angle is going to increase, and this phasor is actually going to spin around. The length of that phasor right there is I sub m, and this is the angle over time. All right, so it's going to turn around 360 degrees like that. Now, if you were to plot the phasor for the voltage, it'd do the same sort of thing. It's going to be right on top of it. Okay, now it may be longer, it may be shorter. I'm just drawing it right on top of it, and that's the point here. And that is the phasor for V. The length of that arrow is the magnitude of the phasor, and the angle is going to be exactly the same over time. Okay, so that's really what's going on here. So you can see that when it comes to V equals I times R, that's really the same thing as I sub m times R, and I sub m angle that is right here again, so we could write this as R times phasor I, and that's what's equal to phasor V. So that's where that relationship came from that you saw right back here for the resistor. Now, for the inductor and the capacitor, it's a little bit more complicated, like I said, but the same idea holds. So let's look at what it looks like for, let's say, the inductor. V for the inductor is going to be L di dt. Okay, well, then if we take this same I right here and we plug it in down here and we take the derivative, let's see, what's that going to be? L times the derivative of that, so that's going to be I sub m. Now it's going to be cosine, so it's going to be sine omega t plus theta sub I times the derivative of what's inside omega, and it's going to be negative, so because it's the derivative of the cosine is going to be minus sine, so that's where minus sine came from. Okay, so we've got that right there. Now this is in terms of a sine function. We can convert that into a cosine function. So let's go ahead and do that. Omega L I sub m times the cosine of omega t plus theta sub I, and then we'll just subtract off 90 degrees to turn it from a sine into a cosine like that. Okay, now this is what V is in the time domain for an inductor. Now remember, we're assuming a circuit that only has one inductor in it and one sinusoidal source that has this is generating that current. So this should be what the voltage is across the inductor at the time. Then we can take the phasor of that, and that's going to be just this magnitude right here. Let's just write that as minus omega L I sub m times angle of this right here. That's going to be the phase angle, theta sub I minus 90 degrees, like that. Okay, well, all of that right there is just the amplitude of the voltage. The negative sign is not part of that, but we could rewrite this as just minus the maximum voltage across that inductor times the angle theta sub I minus 90 degrees, like that. So we could do that right there. Now, if we were to plot that on this complex plane right here, probably a good way to think about this, this is the real axis and this is the imaginary axis. And if I were to plot the I, let's just pick some spot out here. Remember, it's going to turn as time goes by, but let's say that that's I, the length of that is going to be I sub m, but that's phasor I right there. And then the voltage phasor is going to be, what, negative 90 degrees. So you would think that that means it's going to be down here at this angle where that's 90 degrees right there. But that negative sign right there indicates that this is going to flip around. So it's actually going to be up in this direction. And this angle here is 90 degrees. So this is the phasor right there. Now, this is kind of interesting because you'll see as as this thing spins, in other words, as that angle right there increases over time, the relative angle between the V and the I is going to remain fixed. It's not going to change over time for this one element circuit. So they're going to spin together and they're always going to maintain that relative angle right there. So this is an inductive circuit, an L, and the V is going to lead the I. Now, EMF is often used to indicate voltage. So for an inductive circuit, the voltage is in front of the current, and that will always be the case for any circuit that has a dominant inductive component in it, which our example right here certainly would, since there's only one element in it. Okay, keep that in mind. That may be useful to you a little later on. All right, but how did we still haven't gotten to the point where our relationship looks like this. Well, let me show you something. Let's go back to this form right here. Remember, Phasor I, is just I sub m angle theta sub I. Well, if I took J, remember what J is. J is just square root of -1. And on this real complex plane here, where this is the real axis and that's the imaginary axis right there, J is going to be 1 along this axis. So it's going to be right there. Right there. So if that point right there, if I wanted to represent that in rectangular coordinates, it's going to be 0 plus 1j, and that's just j. If I wanted to represent the point down here, which is a negative j, then this is going to be 0 minus 1j, and that's negative j. Okay, so j is 1 angle 90 degrees, and then minus j is 1 angle negative 90 degrees. Okay, so if I take negative j and I multiply it by Phasor I end up with, well, let's see, there it is right there. I'm going to end up with I sub m angle theta sub I minus 90 degrees. Okay, now how did I do that? Well, in order to multiply this times that, you multiply the amplitudes, which I sub m times 1 is just I sub m, and you add the angles. So theta sub I plus a negative 90 degrees, that's where that came from. So that's what we're doing. We're taking this component here and that component there, we're multiplying them together, and we end up with this. Okay, well that is exactly this right here. So let's bring this down and rewrite Phasor V for the inductor is going to be, well, omega times L times Phasor I, and now we got this minus j, we put that up front, and this minus is going to cancel that minus, so we're left with that right there. And that is what looks like this right here. So when we transform from the time domain, if we have an inductor and we want to transform it from the time domain into the frequency domain, the transformation is really straightforward. This is it right here. That's the impedance. And that's a pretty straightforward thing to do. We'll do some examples there, maybe in a minute or two here. Okay, we can do the same sort of thing for the capacitor. If we want to, we might as well. Okay, so for the capacitor, I equals C dV dt. Now once again, we're assuming that there's a single capacitor connected to a sinusoidal source here. And we're also going to assume that we have a voltage equal to V sub m cosine omega t plus theta sub v, like that. Okay, phasor of that, remember if we convert that, is going to be Phasor V is equal to V sub m angle theta sub v. All right. Well, let's take the derivative of this so that we can plug it into our I. So dv dt, well, that's going to be v sub m, that's going to be sine minus sine of omega t plus theta sub v times the derivative of what's inside the parentheses, which is just going to be omega. So there's a derivative, and then we multiply that times c, so we get for our I here, that's going to equal minus c omega v sub m times the sine of omega t plus theta sub v. Now, just like before, it's in terms of a sine. We can convert that into a cosine. So that's going to be minus, I put the omega out front. That's kind of traditional to do that. Omega c v sub m cosine omega t plus theta sub v, and now we subtract off 90 degrees to turn the sine into a cosine. Okay, so we've got that. Then phasor I is just going to be this minus omega c v sub m angle theta sub v minus 90 degrees. Okay. Now, if I do something similar to what I did a while ago, if you remember I have phasor v up here, if I multiply that times minus j, which is 1 angle negative 90 degrees, then minus j times v, phasor v is just going to equal, well, v sub m times angle this plus that, so theta v minus 90 degrees. So this j minus j times v is what that right there is. So this is going to look like this. Let's see. J C omega v sub m. Did I do that right? No, I'm sorry. Phasor v. Like that. So there's the j, the minus signs cancel each other, the j comes out front, there's the omega, there's a c, and that part right there is just phasor v times j. Okay, so we got it. All right, now this right here is in the terms of I is equal to that. We want to put it in the terms of v equals, let's see, that's going to be 1 over j omega c times phasor I. Okay, and that looks like what we've got here. So I'm more interested in what the impedance value is in the frequency domain. Okay, so that's where those relationships came from there. Okay. Now, if I did the same sort of plot here of V and I, then what I would discover is that if I start off with my V and then plot my I, you see the I is going to be theta V minus 90 degrees. Okay, so if V is that right there, notice that this part right here could be written as, well, that's going to be some maximum amplitude. It's going to be negative times the angle theta V minus 90 degrees. And the same idea here, you might think, well, theta V minus 90 degrees, it's going to be back here in this direction, but that negative sign flips that and puts it up in this direction. So this is phasor I. Now this is for an inductive circuit, then that angle is going to be 90 degrees because this is purely inductive circuit. So I said inductive, I meant capacitive. We know, hopefully you realize that. We're dealing with a capacitive circuit here. So for a completely capacitive circuit, the I is ahead of the EMF. Now, put those two thoughts together as Eli, the Iceman, just a little phrase. If you can remember that, and you can remember this corresponds to an inductive circuit, the voltage leads the current. For a capacitive circuit, the current leads the voltage, like that. may be useful to you a little later on. All right. Now we have talked about impedance, and impedance, it has a real part and an imaginary part. The real part here is called resistance. And while you got a resistance, resistance appears in DC circuits as well as AC circuits, but you'll notice over here, this is the reactance. And the reactance can have portions that are contributed by the capacitor, portion that's contributed by the inductor. And if you recall that X sub C is 1 over omega C, and X sub L is just omega L, like that, you notice these two components both have omega in them. That's the angular frequency. Now, for a DC circuit, you're not going to have an angular frequency, or you could say the angular frequency is 0. You could also say the angular frequency is infinity, because they, it has no cycle to it. Well, in either one of those cases, so if omega is 0, then X sub L is going to be 0. If omega is infinity, then X sub C is going to be 0. So this reactance doesn't appear if we don't have some time-varying omega to go along with it. That's why this never showed up when we were dealing with DC circuits, only with AC circuits where we have a time-varying component. Now, just for the sake of completeness, let me say there is something else. This is impedance. Well, there is something else. We would call it Y, and Y is 1 over that. So the impedance is the inverse of this Y component, which consists of, that should be an equal sign there. It has a very similar form to this right here. This G is the opposite or the inverse of resistance, and we've encountered this before, and that's called conductance. So the G is called conductance. And the B is called susceptance. And whereas Z has units of ohms, this has units of 1 over ohms, which is something that we've called S, which stands for a Siemens. Oh, by the way, this Y thing is called admittance. So admittance is the reciprocal of this one here, which is impedance. So that's the relationship. And each one of those are complex values, and they consist of these various parts. All right, so as of this point, you have seen where these relationships come from, and now we're ready to apply this knowledge to solving some sort of problem. Okay, so let's just generate some sort of very simple type of problem. Let's say that I have some impedance 1, some impedance 2, some impedance 3, and then we'll put some voltage AB across this. So this is Z1, this is Z2, this is Z3, like that. Okay, and we're already in the frequency domain here. Okay, well, VAB is going to be the sum of whatever the voltage drops are across this. So VAB, phasor VAB, is going to be I times Z1 plus I times Z2 plus I times Z3, like that. Okay, so we could factor out the I, and we have Z1 plus Z2 plus Z3. So what is this right here? This is just the sum of all of those. So we could write that as some Z equivalent, where Z equivalent is just the sum of these three impedances in series. Now, what did I just show you there? I showed you that Z equivalent for impedances in series is just the sum of the individual impedances, where I is equal to 1 to ever how many impedances you have. So this works for series impedances. Now, that is very similar to the way that series resistors work in the time domain. You will also discover that if we have parallel impedances, then this relationship, Z equivalent, 1 over Z equivalent, is equal to the sum of 1 over the individual Z's from I is equal to 1 to N, like that. Okay, so impedances behave exactly the same way that resistors do in the time domain. So impedances in the frequency domain do that. Okay, so then let's move forward and apply that to a problem. So here's a circuit then that's got 1 resistor, 1 inductor, 1 capacitor. And we'll assign, that's the R, that's the L, that's the C. Let's assign some values. This is our voltage source here. So you notice everything looks pretty much the same that we've encountered before. Let's say R is equal to 90 ohms, L is equal to 32 millihenry, C is equal to 5 microfarad, but this is something we haven't encountered before. Let's make this a time-varying voltage function that is sinusoidal. So 750 times cosine of 5000 t plus 30 degrees volts, like that. Okay, well, if you have a problem like this, one of the first things that you want to do is you want to transform this problem, which is completely in the time domain, to a similar problem in the frequency domain. And the way that you do that is you can redraw this. The symbols still look exactly the same, except now this is Phasor V sub s. And Phasor V sub s is just the Phasor transform of this, 750 angle 30 degrees, like that. Okay, but how do you transform the resistor? Well, the resistor is still 90 ohms. Remember, that doesn't have a complex component. So the resistor is just the resistor. The L is going to be J omega L. So we're going to have J times omega. Well, what's omega? Omega is 5,000 times 5,000 hertz times L. L is 32 millihenries, so that's 0.032. We do that multiplication, and we get J 160. Okay, what about the capacitor? What does the capacitor become when you transform that? Well, I'm putting these arrows here just to indicate that these are not equal to that. You don't have L equal J omega L unless J and omega are 1, and multiplied together are 1. So this is going to be 1 over J omega C. So what does that turn out to be? Well, that turns out to be, by the way, you may not know this, but you may not have recognized it, but minus J over omega C is the same as 1 over J omega C. How did you go from this to that? Well, imagine that you multiply the top and bottom by J. So you got J on top, J on bottom. Well, J times J is the square, each J is the square root of -1. So you multiply the two together, you end up with -1, and you still got that J on top. So there's the negative, and there's the J. So this is equal to that. You can write that in either form, like that. Well, what's this going to be? It's going to be minus J over 5,000 times C, and that's 5 times 10 to the -6. That turns out to be negative J 40, like that. Okay, so this is 90 ohms. This is J160 ohms, and this is minus J40 ohms, like that. So if I want to solve for something, okay, well, I got to figure out what I want to solve for. Well, let's say there's a current here, and that current is I. Then down here, that current is going to be phasor I. So time domain is on top, frequency domain is on bottom. So if I want to figure out what I is just going to be V over Z equivalent. Well, V is given by 750 angle 30 degrees divided by Z, and Z is just going to be the sum of all of those. So 90 plus J160 minus J40. So let's see, that's going to be 750 angle 30 still on top. Let's combine this together. 90, and I'm subtracting 40 from that, plus J120. Okay. Now, we would need to do this division, but you'll notice what we've got here. We've got polar on top. We've got rectangular on bottom. So we need to convert. And if we're going to do, here's the general rule of thumb. If you're going to do multiplication or division, so let me just write that out. If you're going to multiply or you're going to divide, then it's easiest to do it by hand if you're in polar format. If you're going to add or subtract, then it's easiest to do that in rectangular format. So we're going to divide here, so we need to convert this into polar. So this bottom, the top is already in polar, we need to convert the bottom into polar. A few strokes of your calculator will help you do that, and this turns out to be 750 angle 30 degrees divided by 150 angle 53.13 degrees. Okay, now we can do the division pretty easily. It's just the top divided by the bottom. So it's going to be 750 divided by 150. The angle is going to be top angle minus the bottom angle. So that's going to be minus, let's see, 30 minus 53.13 is negative 23.13 degrees. Okay, now this I can't do in my head. 750 divided by 150 is just 5. So 5 angle negative 23.13 degrees. Okay, that's what phasor I is right there. But let's say we were asked to find I, okay, in the time domain. We just found phasor I in the frequency domain. How do you do that? Well, you have to convert back to the time domain to get I. And when we do the inverse phasor transform, it's just going to be 5 times the cosine of, remember the omega stays the same, 5,000 t minus 23.13 degrees amps. There's our answer right there. So the general process in solving a problem like this is perhaps you're given a time domain problem, you convert into the frequency domain, and then once you're in the frequency domain, everything you've learned throughout the semester, all of the techniques of how things combine together works. You just add up things in series and things in parallel, combined like resistors did in parallel. But you solve the same way that you've done problems through the whole semester. So KVL is going to work, KCL is going to work, node voltage method is going to work, mesh current method is going to work. All of those methods are going to work. So let's do a couple of more problems here so that you can see that. Now your life will be a lot simpler if you know how to do fast polar rectangular coordinates on your calculator. And some calculators are smart enough to be able to do complex math. So if you're lucky enough to have a calculator that can do complex math, well, it's even easier. But you got to learn how to do that on your calculator, because I have a feeling maybe you don't know how to do that at the moment. So here's a circuit. Or maybe you do know how to do it. I feel kind of like Bob Ross sometimes. This is our happy little circuit. There's our little resistor, inductor, capacitor, and what we're after is we want to know what the voltage is across that capacitor. Now, we've got some time-varying sources here. This is V is 3 cosine 40t plus 23 degree volts. I1 is 2 cosine 40t plus 49 degrees amps. Let's let R equal 600 ohms. L equals 40 millihenry, and C equals 2 microfarad, like that. Okay, and let's see, we're after V naught here. All right, if we go through the process of solving this, if we didn't have any time-varying sources here, then this would be pretty straightforward. You could do something like node voltage method, where you say this is, well, that's going to be V naught right there. And then you can do write your node voltage equations, and you could solve this. It wouldn't be that bad. The fact that we have these time-varying functions up there, though, destroys that idea of doing it in the time domain. However, if we convert into the frequency domain, then we should be able to do this. All right, in order to convert into the frequency domain, let's see. I1 is going to be 2, I'm running out here, 2 angle, okay, let me see if I can find another pin. Got to go back to my blue here. 2 angle 49 degrees. And this one is going to be 3 angle 23 degrees, like that. The R is still going to be 600 ohms. The L is going to be J omega L, so that's going to be J times omega, which is 40, times 0.040, and that turns out to be J times 1.6. Okay, now that's what L is in rectangular format. If I were to write that in polar format, now these are ones that you should be able to do in your head. This is, remember, keep in mind, you got the real axis, you got the imaginary axis. So this is 1.6 up along the imaginary axis. That's what the J tells you, it's along the imaginary axis, 1.6 up. So this is going to be 1.6 angle 90 degrees, like that. Okay, now we need to do this minus J over omega C, and when we do that, it's going to be minus J over 40 times C, which is 2 times 10 to the negative 6, and that turns out to be minus J 12,500. And that's what it is in rectangular. So if we convert that, that's going to be 12,500 angle negative 90 degrees, because it's down here, 12,500 along this negative J-axis here. Okay, so we've successfully converted all that. Let me write those over here. This is J times 1.6. This is negative J 12,500. All right, we are, and by the way, the V naught transforms into phasor V naught like that, and that's what we're after. Okay, this is our V naught, phasor V naught node. We will choose this as our reference node down here, and I can write V naught minus phasor V1. This is phasor V1. This is phasor I1 over 600. That's the current going down that branch, plus V naught over 1.6 J plus V naught over minus J 12,500 minus I1, phasor I1, that's equal to 0. Okay, now we've got this right here. What we need to do is we need to solve this. Now solving this takes a while because each one of these are complex, so that V naught is a phasor, all right? So think about what you got to do here first. First, you have to take your V naught, you have to subtract off V1, and we got V1 right now. We've got it in polar format. We need to convert it into rectangular, and I just happen to have that already done. 2.76 plus J 1.17. And the same over here. If I need to convert that, I have a feeling I might need that. 1.31 plus J 1.51. I've got them both. I've got pretty much everything in polar and rectangular format now. So go through the process now of subtracting that. Then once you do that, you have to divide. So you have to do the divisions here for each one of those and then subtract off your I1. It's not difficult, but it is kind of tedious, and you do have the possibility of, dropping a sign or two along the way. But you can do that. The issue is also you need to solve for V naught here. You need to get V naught kind of on one side by itself, and say V naught equals something. Well, going through the steps here, you'll discover that that's a little more difficult than what you might first think. All right, so you could do that, though. You can write it this way, though. Let's say V naught minus V1 over the phasor R. So I'm using this symbol right here just to indicate that I've converted the resistor into the frequency domain, from the time domain into the frequency domain, plus V naught divided by, well, what was that? That was the inductor in the frequency domain, plus V naught over, well, what's this? That's the capacitor in the frequency domain, minus I1, and that's equal to 0. Now, the advantage of doing something like this is that now you can go through the algebra steps treating each one of these. You got to keep in mind, though, these are complex numbers, and you can write them in polar and rectangular format, so keep that in mind. But nevertheless, this may help you be able to write it as V naught equals something. And then once you're able to write it as V naught equals something, then you can plug in your values and get the answers. All right? Let me say something else. If you have a calculator that can do the complex algebra, you may be able to plug in this, keeping V naught as your variable, and then solving that. Now, I will show you how to do this, but it's going to take quite a few steps here. So let's get started with this. I'm going to take the approach where I've got V naught minus V1 over R, and these are all phasors. I know I'm going to forget to write the little arrows over the top, so just keep that in mind. Every one of those has a little arrow over the top. So I'm going to start with this right here. Okay. Now, first thing I'm going to do is I'm going to get rid of these fractions down here. And I'm going to do that by multiplying by this one by LC. So what have I got? V0 minus V1 times LC. Multiply this one times RC, so I got V0 times RC plus, and this is also V0 times RL minus I1 times RLC, and that's equal to 0. Okay, so all I did is find a common denominator and then multiply by that common denominator, so I've got this. All right. Now I can factor out V0. I notice I've got a V0 in these first three terms here. I can distribute the LC, so I got V0 LC minus V1 LC plus V0 RC plus V0 RL minus I1 RLC equals 0. Factor out the V0 now. I got V0 times LC plus RC plus RL, and then I can move this other stuff over to the other side. So I've got I1 RLC plus V1 LC, like that. All right, now I can take my V0 and say that that is I1 RLC plus V1 LC divided by LC plus RC plus RL. All right, now at this stage you can go in and you can plug in your values. And it's not trivial from this point forward. Like I said, it's not difficult, it's just tedious. All right, so I1, I wish I hadn't written those on the opposite side, but I1 is going to be 2 angle 49 degrees, that's what I've got, multiplied by R, which is 600. By the way, it's 600 angle 0 degrees. We'd leave off the angle 0. Multiplied by L, which is 1.6 angle 90 degrees, times C, which is 12,500 angle negative 90 degrees, plus V1, which is 3 angle 23 degrees. Is that what that one is? 3 angle 23 degrees, yep. Times L, which is this one, 1.6 angle 90 degrees, times C, which is the 12,500 angle negative 90 degrees. I know I'm running out of room here and you probably can't see that. I'll scoot over a little bit. Divide that by all this stuff, which is 1.6 angle 90 degrees times 12,500 angle negative 90 degrees plus 600 angle 0 times 12,500 angle negative 90 degrees plus 600 angle 0 times 1.6 angle 90 degrees. Okay. You need to do the multiplications here. And remember the way that this works. The way it works is you take the amplitudes, you multiply them together. The angles are added. So it's going to be 49 plus 0 plus 90 minus 90, and it's going to end up just being 49 degrees. But it's going to be 2 times 600 times 1.6 times 12,500. If I've done my arithmetic correctly, that's 24 million angle 49 degrees. Plus, now this turns out to be 60,000 angle 23 plus 90 minus 90, 23. Divided by, now you've got to do the same thing for each of these three terms that are on bottom. And this is going to be 20,000 angle 0 degrees plus This one turns out to be 7.5 million. Angle negative 90 degrees plus 960 angle 90 degrees. That's a degree mark there. All right, now we need to do additions here. So in order to do that, we need to convert each one of these into rectangular. So when I do that, for this component here, I get 1574516.7 plus J1811302.9.93. That's just this first term here. Plus, now the second term, 55230.29 plus J2343.87. Of course, I'm looking at my notes. I can't do that in my head. Divided by, now I need to do the same thing for each of these three terms down here on bottom. By the way, this one should be easy. You notice that that is an amplitude with a zero angle, so that's all along the real axis. That's just going to be 20,000 plus J0 if you wanted to write that, or you could leave that off. Plus, now this one is going to be real easy too, because that's the negative 90. That's going to be all along the negative J axis. So it's just going to be 0 minus J 75 or 7.5 million. 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. Plus, now same thing here. This is going to be 0 plus J 960, like that. All right, so we're ready to combine things. So you combine the real parts, you add the real parts together, and you add the imaginary parts together. So on the top, we're going to end up with 1580064.99. You may get slightly different numbers if you round. Plus J1813647.3.8 divided by, and now we combine the bottoms, and we get 20,000. There's only that real component right there. And then these two components here, minus J 74,99040. Okay. All right, we've combined those, and now we've got rectangular on top, rectangular on bottom. We need to do this division here, so let's convert those into polar. And when I do that, I get 2405394.2.03 angle 48.9 degrees divided by 7499066.67 angle negative 89.8 degrees. Now you do the division, and when you do that, you end up with 3.2. Top fraction minus the bottom fraction, I'm sorry, top angle minus the bottom angle is 138.7 degrees. Okay, this is our V naught. Assuming I didn't make an algebra mistake somewhere along the way, that's our V naught right there. Now we still haven't solved the problem, because the problem was to find this V naught in the time domain. We found Phasor V naught in the frequency domain. So all we need to do is convert back, and when we convert, that's pretty straightforward. This is the amplitude and that's the phase angle. So our V naught is going to be 3.2 times the cosine of, now omega t, I've forgotten what omega was. Omega is 40. So 40 t plus 138.7 degrees volts. There is our final answer. Okay. All right. So there, we just found that, and it was kind of tedious to get through all of the algebra, but nevertheless, we were able to do that. I think that'll be the only one I do right now. I'll do some more problems perhaps in the next video. You need to get used to using the complex functions or perhaps the polar to rectangular functions on your calculator. You can do this by hand. Like I said, it takes a long time and it's kind of tedious, and it's prone to produce algebra mistakes along the way. But I do that. See if you get this same answer that I got, and if not, let me know. Maybe it's entirely possible I made a mistake somewhere in there. So double check me on that, and then get back to me if you think it's a mistake, and I'll redo it myself. But I am going to do a few more problems, but that's next video. Okay, see ya.